Okay, let's get back going here. Let's take a look at, I had skipped G. G has a C2 axis of symmetry. So you got one methyl on top, one on bottom. So G is going to have three signals. The two methyls are equivalent because of the C2 axis. C2 axis is 180 degrees. That makes those two methyls, my markers there, the equivalent. The two hydrogens then would also be equivalent that are right there. And then these two would be equivalent, but these two are different than the other because these two, because you got the C2 axis, that makes these two equivalent, whereas they were different here. So this one would have three signals, this one has four signals. Let's go up to I. How many should I see for I? Now I is very similar back here that we did with C. Watch that double bond. So how many signals should I see for I? Six. Very good. 6 is correct. We got the CH3. That's one signal. We got the CH2 right next door to it. That's another signal. We got another CH2. That makes a third signal. Those two CH2s are not equivalent. One of them's close to the double bond, one's not. They are different. And then you got the three hydrogens on the double bond are all different on the alkene because there's no symmetry in that alkene. So all three of those hydrogens are non-equivalent. So it's got six hydrogens, six different hydrogens. We would have six signals. J is very straightforward. CH2 gives a signal, CH gives a signal, CH3 gives a signal, and OH gives a signal. So you got four signals for that one. That was very easy. K is easy. You got 1, 2, 3. Three signals on K. Very straightforward. L is very similar to what we did down here for H. So you got 1, 2, 3, 4, 5, 6. You got 6 on that one. Because you got some above the ring, some below the ring. So that makes those different. Because some of them are up there with the methyls that are on top. Some of them are on the bottom with no methyls, so it makes those different. Let's go down here to M. I want you all to do M. How many protons, how many signals will I see for the protons in M? Somebody over here. Now, he's been answering everything. You all, somebody over here answer.
7.
I hear 7. I have a different answer. How'd you get to 7? How you got 7?
5.
Okay, I hear 5. The answer's in between the two of you. 6 is. Oh, it is 5. Sorry, 5. It is 5. You're 5. You're right. I miscounted there. Okay, this has a plane of symmetry through here, through the ring. This methyl gives a signal, but that methyl's different than this methyl, because this methyl's on a CH2, this is on the benzene ring. So you got this methyl, you have the CH2, and the other methyl, it makes 3. Now you have symmetry through that ring, that makes the top equivalent with the bottom here, so this hydrogen's equivalent with this one. That gives us 4 signals. And then this hydrogen is equivalent with this one. That makes 5 signals. But these are different. See, these two are next to a methyl group. These two are next to an ethyl group. So that's got 5 signals. That's correct. 5 signals for that. And there is no hydrogens on these carbons. Maybe that's how you get, I don't know if that's how you got to 7 or, but there is no hydrogens there. Okay, now, N, very straightforward. You got the methyl gives a signal, The CH there of the alkene gives a signal, and that CH2, those two are equivalent. So they give a signal. That's got 3. Let's do O. How many would we have for O? O has a C2 axis. There is a C2 axis right through the center here. If you rotate 180 degrees, you have the same thing. Three. Because if you rotate 180 degrees, that makes these two methyls equivalent. These two CHs are equivalent. And then these two methyls are equivalent. So I've got 3 different signals. How about, let's go ahead and do P while we're at it. It also has a C2 axis of symmetry right through the center. Okay, this is how you get to the 4. Because of that C2 axis right down the middle, you rotate 180 degrees, same thing. It makes these two methyls equivalent. That makes this hydrogen equivalent with this one. These two are equivalent. And then these two are equivalent. So it gives me 4 signals. So the number of signals tells us how many different kinds of hydrogens we have. How many different environments that they're in. We're next going to look at the chemical shift. So the chemical shift is where it comes on the x-axis. So the chemical shift, where it comes on the x-axis, is telling you something about the environment that it's in, what's around it, what's around that hydrogen. Certain things will move that signal one way or the other. So where it comes on the x-axis telling you a little bit about what's around that hydrogen. Now, protons can either be shielded or de-shielded. Shielded, what we're talking about, we're being shielded from feeling the full effects of the magnet. That's what shielding is. It doesn't feel the full effect of the magnet. There's certain things that will shield a proton. Other things will de-shield a proton. So it's raining outside this morning, so let's think about that. I'm going to use that as my example. Shielding, a proton that is shielded, is like you going outside in the rain with an umbrella. You are shielding yourself from the rain. So a proton that is shielded, it's like it's got an umbrella. It's being protected not from rain, but from feeling the big full effects of the big magnet. De-shielding is just the opposite effect. Not only is it feeling all the rain, it's like going outside and you got no umbrella and you're getting every bit of the rain on top of your head. Not only are you feeling that, you've got some mean person behind you with a water hose spraying you as well. So you're feeling the rain plus a water hose. You're feeling more than what you really should. That's de-shielding. So protons can either be shielded or de-shielded. And that's going to affect where they're going to come on the x-axis. So, let me show you which way things are going to go. Things that are shielded, they move upfield. That's to lower ppm values. That's the upfield end. I know that seems weird. Upfield is going to smaller numbers, but that's the way it goes. So this is the upfield end. This is your high field strength. This is your low field, but the ppms are switched on that. So Your high field is low ppm values. Your low field is the higher ppm values. I know that's counterintuitive, but that's the way it goes. So things that are shielded are going to be shifted in this direction. If it's something that's de-shielded, it's going to go downfield toward the higher ppm values. This is your downfield region. That's things that are de-shielded. Now, let me go ahead and just pass out. I've got a little summary sheet. It's also here in the slides, but I went ahead and printed it out for those of you that are here. But if you're watching on the video, it is on the slides on Moodle there. So this is a little summary. Supposed to have my mask on when I come around there. I like my little summary better than looking at these numbers on the slides. So if you know this little summary chart, this will get you by as far as test purposes go. I think there's 3 there. Okay, if you have a normal alkane proton, you got nothing else in there except just a normal alkane. You don't have any carbonyls or double bonds or bromines or anything like that. Just a normal plain alkane. Normal alkane protons come from about, like I said, I don't really like the numbers that's here in the slides. This is just what came with the textbook. I remember 0.5 to 1.5. That's easy for me to remember. 0.5 to 1.5, and that's what I've got there on the little summary chart. If you have I'm just going to go with my summary chart. Do I have I like that part though. Okay. We'll come back to that. Let's go over. I'm going to stick with the order the slides are in. So it's jumping around here on my chart. But if you have protons on a carbon that is connected to an electronegative atom, they come from 2.5 to 4.5. Now I know this says 3.1 to 4. I just say 2.5 to 4.5. That's just easy to remember again. Now, as to what that electronegative atom is doing, it's de-shielding. Those electronegative atoms are de-shielding the proton. And so that shifts it downfield to higher ppm values. The more electronegative it is, the atom, the more it gets shifted downfield to higher and higher ppm values. So that electronegative atom, what is happening is these electronegative atoms they've got this electron density, electronegatives pulling electrons toward it, and then those electrons get to spinning in the magnetic field. They get to spinning and they create their own little mini magnet. So your proton not only feels the effects of the magnet in the spectrometer, it feels the effects of those electrons that are spinning and creates the little mini magnet. It feels that magnet as well. So that's why it's de-shielded. It's feeling, like I said, it's like feeling the rain, the big magnet, and somebody spraying a water hose on you. That's the little mini magnet from the electron spinning. And the more electronegative that atom is, the more of effect it's going to be. The more they're spraying you with a water hose if it's more electronegative atom. So you can see if you have a higher, hydrogen on a carbon that's connected to, say, a fluorine, or most electronegative, then it's going to get shifted the furthest downfield. Downfield is this direction, to about 4.2 or so. Now, oxygen is our second most electronegative atom. So if you have a hydrogen on a carbon that's connected to an oxygen, then that gets shifted down to maybe 3.4 or so. Chlorine is our next most electronegative atom. Maybe that's around 3. So where it comes, that will tell you something about the electronegativity. That electronegative atom is shifting those protons downfield. So again, hydrogens on a carbon that's connected to some electronegative atom, about 2.5 to 4.5. That's just a good, easy area to know. 2.5 to 4.5. Okay, book really jumps around here on these slides. Let's go all the way, let's jump on down. We'll come back to some of these others in a moment. Let's jump on down. Again, I don't like their list. It's easy for me to remember. 6.5 to 8, or you could even make that 8.5 if you want to. You rarely see them all the way up there, but about 6.5 to 8. Those are protons on an aromatic ring. Now, we recently learned in lecture about aromaticity, and we went through all of these rules of aromaticity, but there's always exceptions to every rule. So when we make a brand new compound in the lab, how do we prove that this molecule is aromatic? Right here is how you prove. You go take an NMR. And if you have protons down there in the aromatic region, then you know it's aromatic. So this is how we prove whether a molecule is aromatic or not. Go take an NMR spectrum. So if you've got protons in that 6.5 to 8 region, more than likely it's aromatic. That's giving you some proof that you have an aromatic compound. Now I'm going to back up just a little bit here. From about 4.5 to 6.5, I know they say 4 to 6 here, but I say 4.5 to 6.5. That's protons on a carbon that's involved in a double bond. That's a proton on an alkene, directly attached to an alkene. That's from 4.5 to 6.5. Now we had skipped another one. By the way, I had a slide here. I didn't realize I had that. So that aromatic ring, those electrons get to spinning that's in the ring. We talked about how those spin around and around the ring. Well, they get to spinning so fast, they make their own little mini magnet. So that de-shields those protons that are coming off. They feel the big magnet plus the little mini magnet, because those electrons are spinning around, creates a little mini magnet. So that gets those de-shielded. That's why they're shifted all the way down there to 6.5 to 8. Well, the book didn't have these on there. I didn't see them. Nope. Okay. These are important. 1.5 to 2.5. 1.5 to 2.5. That's a proton on a carbon that is connected to another carbon that's involved in a double bond. You're not on the double bond, you're on a carbon next to the double bond. 1.5 to 2.5. If it's the proton on the double bond, you're down here 4.5 to 6.5. But if you're on a carbon that is connected to a double bond, then you're 1.5 to 2.5. Now that double bond, it doesn't matter whether it's an alkene or a carbonyl, as long as it's a double bond there. It doesn't matter. So if you're a proton on a carbon that's connected to a carbon of a double bond, you're 1.5 to 2.5. An alkyne proton, that's around, if you have a proton on an alkyne, that's about 2.5. And then some others that weren't here on the the book slides. All the way down there, about 9.5 to 10, is an aldehyde proton. That's the proton directly attached to a carbonyl. And then even higher, 10.5 to 11, that's a carboxylic acid proton. Now, we have another one to deal with, and that's alcohols and amines. Alcohols and amines are all over the place. They're anywhere from 0.5 up to 5. So on your chart that I have, that's all the way across there. That's a proton on a nitrogen or a proton on an oxygen. Your alcohols and your amines. They are all over the place because of hydrogen bonding. It really depends upon how much hydrogen bonding is doing as to where its location is going to be. So the more concentrated your sample, you're going to have more hydrogen bonding. If you have more dilute sample, then you're going to have less hydrogen bonding. So they will come at different places depending on your concentration of your sample. So they're variable. They're all over the place. Now, you might say, well, that causes me problems, doesn't it? It's over top of all of this other stuff down here. Well, just like an IR, remember the NH and an OH, an IR, is really, really broad because of the hydrogen bonding. The same thing happens in NMR. It's going to be a very broad peak because of that hydrogen bonding. So it's very easy to pick out an OH or an NH because it's a broad peak. So even though it may overlap some of their other stuff, it's easy to tell the difference. All these other peaks are going to be very sharp, very narrow peaks, and your OH or NH will be very broad. Easy to tell the difference. Now the book gives you a chart this way if you want more specific numbers, but I think if you know my little summary chart, that's good enough. That's all you're going to need to know. Yeah.
So how do you tell the difference between an OH and an NH if they're both broad and they both come in that area?
OH, if you were to have both in a molecule, OH is stronger hydrogen bonding. You have stronger hydrogen bonding on oxygen just like we did in IR. So if you remember what we talked about in IR, an OH is much broader in IR than the NH. It was broad, but not as broad.
Yeah.
Same thing here with NMR.
Okay.
The OH is going to be much, much broader than an NH. So I don't like it listed this way. If you just know my little summary chart, you will be in good shape. So I have the summary chart. I think that's on Moodle, I think, or it's here in these slides. I can't remember. Let me just look real quick. I have it here in the slides somewhere. So it's on the Moodle. My summary chart should be listed as a separate file on Moodle. I'll check that as soon as I finish here, just to make certain that I have it on there. For those of you watching the video. So it will be on Moodle. Okay. Any questions on chemical shift? So let's see if we can apply this to a problem here. Now, with my summary chart, don't get locked into this. This is just a typical place where things come. Not everything is typical. So don't get locked in thinking, it has to be this. This is what my chart says. No, this is a starting point. It doesn't have to be this. But this is a good place to begin. A good rough estimate to start with. Now, let's take a look at an example here. So if we look at our molecule that we've got here, we've got two different kinds of protons because of the symmetry. You have symmetry this way, and you also have symmetry this way. Symmetry this way makes the methyls equivalent. So that gives one signal. It makes these two hydrogens equivalent. The ones on the bottom equivalent at the top. But then symmetry this way makes this side equivalent to this side. So all four of those blue ones are equivalent because it's got the two symmetry elements. So we've got two different kinds of protons. I will have two signals. And you can see that here. I have the signal for the pink ones and I have the signal for the blue ones. Let's look at the chemical shift. So we just talked about the chemical shift. The blue protons are on an aromatic ring. So I said protons on an aromatic ring come from 6.5 to 8. 6.5 to 8. Yep, right there. There we are. It's about 7.1. Perfect. That's our aromatic protons. The pink ones, they're on a carbon that is connected to a carbon that's involved in a double bond. I said that's 1.5 to 2.5. If you look on the chart, 1.5 to 2.5 protons on a carbon that is connected to a carbon of a double bond. 1.5 to 2.5. And we're perfect. It's about 2.3 there. Perfect. So our chemical shift is good. By the way, there's our TMS. That's our reference compound coming right at 0 ppm. That's our reference compound. So everything's referenced to that, so we know the exact position of these peaks because that's set to 0. Any questions on that? Now, there's something else on this particular spectrum, and that's going to lead us into the next topic. These little lines here. This little line. These are called integration lines. This is integrating from 1 to 1.5. Now the computer, when it does integration, so your integration is giving you the area under the signal. You're going to measure the area under each signal, and that area under each signal represents how many protons are associated with that signal. Now, it doesn't know exactly, the computer does not know how many protons are there. It doesn't know what your molecule is. So what it gives you is a ratio. This is just a ratio of protons. So you saw in that previous example that I had there, the integration was saying 1 to 1.5. There's no such thing as 1.5 protons. So double it. It could be 2 to 3. The ratio is 2 to 3. Or it could be, as you look at the actual molecule, is actually 4 to 6. It's just a ratio. That's the same ratio numbers. So it will give you the ratio of protons by looking at the area under the signal. Now, we are measuring the area under the signal, not the height of the peak. The height of the peak does not matter. But the area under the peak does. Because there's things, like I mentioned, like hydrogen bonding broadens, makes those OHs like broad. So what that does, when you broaden the peak out, it makes the peak shorter, but the area underneath did not change. So that's what we measure. So the height of the peak does not mean anything. It's the area under the peak is what means something. So our integration is measuring the area under the signal, and that will give us the ratio of protons. So if you were to look at this molecule that I have up here, there's two different kinds of protons there. And if we integrate that, we should have two signals, and if we integrate that, it's going to integrate, the computer is going to say 1 to 1.5. Because what it always does is make the smallest one just equal to 1, because it doesn't know any better. It just says, my smallest integration, I'm going to set to 1. And then it adjusts everything based off of that. So it's going to say 1 to 1.5. Well, again, there's no such thing as 1.5 protons, so just double it. So instead of 1 to 1.5, it's 2 to 3. And that's exactly what that is. It's 2 to 3 is the ratio. So it's measuring the area under the signal. So it will integrate that and it should come out to 2 to 3. Now, you can measure this by hand or you can let the computer do it. So on your exam, the numbers may not be given. It may just have the integration lines. These are the integration lines. So what you're doing, your integration lines, you're measuring from the flat region to the flat region. You measure that distance and compare it to this flat region to this flat region. If you look at this signal, the area height here, the area height of that signal, this you can see it's about a 2 to 3 ratio. And you can do that with all of the protons down the list. Doesn't matter what your units are because you're just doing a ratio. You can measure it in inches or centimeters or millimeters or whatever, it doesn't matter. Or you can just eyeball it. So, if you've got something integrating for 2 protons, more than likely, my first guess, if it's integrating for 2 protons, I'm going to guess that that's a CH2 group. If it's integrating for 3 protons, I'm going to first guess that's a CH3 group. Now that doesn't have to be the case. You know, if it's integrating for 2, I guess that it's a CH2, but it could be 2 equivalent CHs. If they're equivalent, they come at the same place, and that would integrate for 2 protons. If you got 2 CHs that are equivalent, but my first guess is going to be a CH2 group. Integrating for 3, my first guess is that's a CH3 group. Could be 3 equivalent CHs, but what's the likelihood of having that in a molecule? More than likely it's a CH3. That's my first guess. Okay, any questions on the integration? That integration is important. Look at the integration, please. So like I said, if it's integrating for 2 protons, I'm going to guess it's a CH2 group. Integrating for 3, I'm going to guess it's a CH3 group. Integrating for 6, I'm going to guess it's 2 equivalent CH3s. Could be 3 equivalent CH2s, that would get me to 6. But that's pretty tough to have 3 equivalent CH2s. More than likely it's 2 equivalent CH3s.
I have a question.
Yes.
On the last slide, it integrated for 2 HA protons over the HBP, but 3 HB protons over the HAP. Are those supposed to be swapped?
No. What it is, that is leading us to the next topic. This is not representing that this is yeah, they've actually, it's leading into the next topic. They're talking about the splitting. So this splitting is due to the blue protons, and this splitting here is due to the red protons. We'll deal with that in the next slide.
Okay.
This is the blue protons and this is the red one. But the splitting is due to your neighbor. So this splitting into 3 lines is due to the red. Even though this is the blue the blue gave the signal, but the red done the splitting.
Okay.
Your neighbor is going to do the splitting. So that leads us into the next topic. We're going to look at this splitting of the lines. So this back here had 2 signals. There's 2 signals, but each signal is split into several lines. And the splitting is due to your neighbor. Your neighbor does the splitting. It's called coupling or signal splitting. It means the same thing. You can call it coupling. It couples to the neighbor, or it splits the neighbor. Now, this splitting or coupling has to be very close by. It can't be anything very far away. It needs to be within 2 or 3 bonds to do a splitting. And it has to be from non-equivalent protons. Equivalent, write this down. Equivalent protons do not split each other. Equivalent protons do not split each other. To have the splitting, they must be non-equivalent. Now, I'm going to, let me get my mask on because I got to get close to somebody here. So you must be within 2 or 3 bonds to do the splitting. So let's say I've got a big old axe, and I'm mad at him, and I'm going to split him in half. Now I've got to be close, or my axe is not going to do anything. If I'm all the way over here, my axe I can't reach him. You got to be within 2 or 3 bonds to do the splitting. So you got to be close enough to do the splitting. But you're only going to split non-equivalent protons. You're not going to split equivalent. Splitting equivalent is like splitting yourself. You're not going to split yourself. That's like splitting equivalent protons. You're not going to split yourself. So equivalent protons do not split. It's got to be something different. You need non-equivalent protons. And you got to be within 2 or 3 bonds. So for our purposes, you need to be, what's doing the splitting must be a proton on an adjacent carbon. Any further than that, it's not going to split. It must be the next door carbon. Protons on the next door carbon, on the neighboring carbon. And that would be 3 bonds away if you count. So if you got a hydrogen and it's on a carbon, and then you look at another carbon and it's got a hydrogen, those would be 3 bonds away from each other, so those hydrogens will split each other. So that would get us 3 bonds. Now, how many pieces am I going to split him into? The rule follows n plus 1. That's the number of lines that you're going to see follows the n plus 1 rule, where n is the number of protons on your neighboring group that's doing the splitting. Remember, it's got to be on an adjacent carbon, your neighbor, and how many protons are there. That's what we're going to plug in for n. So that tells you how many lines it's going to be split into. So let's look at an example here. So this has 2 signals. You have the blue protons and you have the red protons. So I'll have 2 signals. And then your neighbor does the splitting. So the red protons will split the blue protons, and the blue ones are going to split the red ones. So back here on him, not only am I going to hit him with an axe, he's going to turn around and hit me back with an axe. So we both get split. Now, your splitting follows that n plus 1. Okay, so we've got the red protons. The red ones are going to give a signal, but they're split by the blue ones. How many blue ones you got? You got 3. So you plug 3 in to our formula, n plus 1. So 3 plus 1. So the red ones will show up as 4 lines, or that's called a quartet. The red protons are going to show up as 4 lines because they're being split by 3 blue ones. Now the blue ones will also give a signal, and they're going to get split by the red ones because they're on an adjacent carbon. They're a neighboring. So we've got 2 red ones. We'll plug 2 in for n. 2 plus 1, we see 3 lines, or that's called a triplet. So that splitting tells us what our neighbor looks like. How many hydrogens is on the neighboring carbons? Let's look at another one here. So this one here, we've got the pink and the green protons. So I've got 2 signals. And the pink's going to split the green ones, and the green ones are going to split the pink one. So the pink one will give a signal, and it's going to get split by the green ones. There's 2 green ones, so we'll plug 2 into the formula. So that pink one is going to show up as 3 lines, or a triplet. The green the green protons will give a signal, and they're going to be split by the pink one. We only have one pink one, so we'll plug into our formula. N plus 1, so 1 plus 1, 2. That's called a doublet. You have 2 lines. So the green ones will show up as 2 lines, a doublet. Because there's only one proton on the neighboring carbon that is splitting it. So let's look at an example here of a molecule. This is the same molecule. They switched colors on me for some reason. This is this one down here. They just switched colors on me. But it's still that same molecule. So we saw we had supposed to have a doublet and a triplet. So let's see what we got here. Let's see if everything makes sense. So we got 2 different kinds of protons. You got the red and the blue. So I got 2 signals. And you see I have 2 signals. Now the computer is not going to have them in color for you. It's all everything's going to be black. Because they didn't know which one's